Okay, so today we're still talking about equilibrium, but we're going to talk about something called a Rice table, which I know sounds ridiculous, okay, but that's what it's called, okay? And when we set it up, you're going to see why it's called that, all right? But the example says, calculate the value of Kc, so the equilibrium constant, for this reaction, and we have our reaction, 2CO plus O2 is in equilibrium with 2CO2. If the equilibrium concentration of CO2 is 0.15 molar, assume the initial concentration of CO is 0.25 m, and the initial concentration of O2 is 0.40 m. So when you have only equilibrium concentrations for some of the substances in your reaction and you have initial concentrations of others, you're going to have to do a Rice table, okay? And so I'm going to set up R-I-C-E, okay? So R stands for reaction. So we're literally going to write down the reaction. And you want to space it out some because you're going to be writing some stuff underneath. So you don't want to put it super close together. Okay, I do want to warn you that these problems are probably going to take up half a page to a page on their own, each one. So just be aware that you're probably going to be using quite a bit of paper. Okay, it's just the way that it goes. And then the rest of it is 2CO2, also a gas. Okay, notice they're all gases. They'll all be included in the equilibrium constant expression once we write down our information. Okay, the next thing that we need to talk about, so R stands for reaction, and then I stands for initial. Okay, so what's our beginning amounts? Okay, so this at equilibrium is not an initial. Okay, so our initial, it says the initial concentration of CO is 0.25 m, so 0.25, and the initial concentration of O2 is 0.40. Okay. So in your Rice table, they always need to be concentrations, okay? They should always be molarities, all right? And then we don't have an initial concentration of our CO2, but I want you to think about this. The way this reaction is written, these things here on the left are my reactants. These are what I have to start with. Well, when I start the reaction, I don't have any product. So my initial concentration of a product is always going to be 0. If there was more than one product on this side, both of them would be 0. Okay, so your reactants will have initial concentrations and your products are going to be 0 because they don't exist yet. All right, and then C stands for change and E stands for equilibrium. Okay, so I'm going to draw a line in between C and E, okay, because equilibrium is kind of our goal. All right, now all we know is the equilibrium concentration of CO2. Okay, so we can't write that in our table yet, though. We're going to use it in our equilibrium constant expression, but we can't write it in our table yet. And since we don't know how much these are changing by, we're going to use a variable, and we're going to use x, okay? I know that's super shocking, okay? So the thing you do need to notice, though, is that reactants are getting used. So their change over time is going to be subtracted, okay? So we're going to subtract x from our reactants, okay? So notice I just did minus x on this one. There's a 1 in front of this balanced one, so it's just one of the x's. But here, there's a 2 in front. So this is gonna be minus 2x because it's gonna change twice as much, okay? And then our product, since it's getting created, the change is gonna be x, but again, there's a 2 in front, so we're gonna add 2x, okay? So let me go over that again. R stands for reaction. You just write down your reaction as is. I stands for initial. So those are your initial concentrations. Your reactants should have numbers. Your products should not. It should start at 0. They do not exist in initial concentrations first. Okay. C stands for change. Okay. You're going to change by an amount x. Okay. If there's a number in front, it'll be 2x. If this was a 3, this would be minus 3x. Whatever is in front is how many x's you subtract from the reactants because they're getting used. The products, you're going to add x. If there was a 1 in front here, this would be just plus 1x. If this was a 4, it would be plus 4x. Whatever that number is gets added on the product side. Same thing if there was another product, okay? So now when I write my equilibrium, this is what I know. I know it's 0.25 minus 2x. That's what I know that equilibrium concentration is equal to. This equilibrium concentration is equal to 0.40 minus x. Okay? This equilibrium concentration is just equal to 0 plus 2x, which is 2x. Okay? So we haven't really used any numbers just yet. Just try to make sure you understand where this stuff came from. So I literally just wrote down 0.25 minus 2x. Again, we subtracted from the reactant side because those concentrations are being used over time. We add to the product side because they are being created. Starts at 0 and gets created, starts at 100% and gets subtracted. Okay, so now what we need to do is look at our other given information. We know the equilibrium concentration of CO2. We know this concentration. So we know, let's switch colors. We know that 2x equals 0.15. Okay, because it told me the equilibrium concentration of CO2 is 0.15 m. Okay, so I could solve for x by dividing by 2. So x equals, so 0.15 divided by 2 equals 0.075. Okay, so that's not really an answer. Okay, I'm asking for the value of the equilibrium constant. So in order to do that, I actually need concentrations for all 3 of my species or my substances. Okay, so what I'm going to do first is write an equilibrium constant expression. All right, so I'm going to say Kc equals, and remember, equilibrium constant expressions, only gases and aqueous get included in the equilibrium constant expressions. Pure liquids and solids do not get included. So all 3 of these are gas, so they're going to be included. So I'm not going to write numbers yet. I'm just going to write the expression. So this would be CO2. Remember, it's products over reactants. And since there's a 2 in front, we're going to square it. Divided by, and then our 2 reactants, CO squared because of the 2 in front, and then times O2. Okay, so that's what our equilibrium constant expression is. Okay, now we know that the equilibrium concentration of CO2 is 0.15. Okay, so Kc equals 0.15 squared. We know that much. Okay, because it told me the equilibrium concentration of CO2 is 0.15. We also just solved for x, because we knew that CO2 was 2x at equilibrium. So we said 2x equaled 0.15, divided that by 2, which gave me 0.075. But I can use that information to solve for concentrations of these guys and plug them into the expression. So I'm going to do 0.25 minus 2 times 0.075. So let me back this up. This is 0.025 minus 2 times x, and x equals 0.075. So that's where that came from. So I'm going to use my calculator to get some answers. So 0.25 minus 2 times 0.075. So 0.25 minus, and this here we know is 0.15. So basically 0.25 minus 0.15, right? That's what 2 times 0.075 equals 0.10. So that is our concentration of CO. That's what we were just solving for right there. This is CO's concentration. Okay, so we're going to plug that into our expression over here. So 0.10, and we're going to square it because that's what our expression said to do because of the 2 in front. All right, so then over here, we're going to figure out the concentration of the O2. It starts out at 0.40 minus, and it's just 1x. It's not 2x this time because there was no 2 in front. So minus 0.075 because that's what x equaled. Okay, so 0.40 minus 0.075 equals 0.325. So that is our concentration of O2 at equilibrium. So I'm going to plug that in over here. This one doesn't get squared because there was no 2 in front. It's just going to be normal. Okay, so now we can type all of this in and get an answer. So 0.15 squared divided by 0.10 squared, and then I'm going to divide again by 0.325. Okay, so I got KC equals, and everything I gave you in the information is 2 sig figs, so this is what my calculator gave me. And I'm going to round that to 2 sig figs, so this is going to be 6.9. So, like I said, takes up a lot of space. Okay? Like I said, takes up a lot of space. You have to be able to write an equilibrium constant expression. If you can't write one, you need to email me or contact me in some way. Okay? Because this is so not where we're at right now. We are moving way past that. Okay? So I'm going to do another one. You can always rewatch any part of the video that you need to. This one's going to be slightly different, but similar. Okay? We're still going to do a rice table. All right, so it says a mixture of 2HI, and it's a gas, is in equilibrium with I2 as a gas plus H2 as a gas. Okay, initially contains 0.75 molarity of HI. At equilibrium, the I2 is 0.300 molar. Calculate the equilibrium concentration of HI and the value of KC. Okay, so I'm going to go ahead and start a rice table. So I have R, I, C, E. Reminder, R stands for reaction. So I'm literally just going to write down the reaction as is. 2HI as a gas. It's an equilibrium with I2 as a gas plus H2 as a gas. Okay, that's what R stands for, reaction. Now, I stands for initial. So the only information we have about initial concentration, initially contains, is for our HI. So we know this is 0.75. Okay, and it's a molarity, so we're going to leave it. And then we have an equilibrium concentration, and we're asking for the equilibrium concentration of HI and the value of KC. So I really know nothing else for my table, okay? But I do know that since this is a reactant, that means these are products, since they're on the right side of this arrow, and that means their initial concentrations are 0. All products initially are at 0. All reactants are initially at something. That should be given to you. Okay? So again, I stands for initial. All right? C stands for change. So we're going to change again by X. But remember, if there's a number in front, we're going to multiply that X by that number. Reactants are getting used. So we're going to subtract 2X from any reactants. And the 2 is because of the 2 in front of the HI. If there was no number here, we would just do minus X. Okay? Products. Since they don't have an initial concentration, we can't subtract. We can't have negative concentration. So what we're going to do is we're going to add X to each. Neither one of these has a number in front, so it's just 1X apiece. I'm going to draw my line. All right, E stands for equilibrium. So let's write what they're here, and then we'll see what numbers we can plug in. So this is going to be 0.75 minus 2X. Over here, this is going to be 0 plus X, which is X, and 0 plus X is X. Okay? So let's see what else we know. All right, if we go back and read, it says it initially contains 0.75 molarity of HI. We used that, so check. We used our reaction. All right, the next thing we were given is this at equilibrium. The I2 concentration is 0.300 molarity. So we know here that I2 at equilibrium is 0.300 m. Okay, and it is equal to X. So X equals 0.300 m. That's our molarity. Okay, well, if I2 is X at equilibrium, and we know the number, H2 is also X at equilibrium, and we also know that number. So that means H2's concentration is 0.300 molarity as well. Okay, and we can use X to solve for the concentration of HI at equilibrium. Okay, so we're going to do 0.75 minus 2 times, and then we're going to plug in X, 0.300. So I'm going to use my calculator, 0.75 minus 2 times 0.300. Okay, so 2 times 0.3 is 0.6, so 0.75 minus 0.6 is 0.15. So that's our equilibrium concentration of HI. All right, so I'm going to write the equilibrium constant expression first. So Kc equals, all three things are gases. They all get included. If one of them was a solid or a liquid, we would not include it in our expression. Okay, so it's going to be products over reactants. So I'm going to start with I2. There's just one of them, so I don't need to raise it to a power. Then I'm going to do H2. There's just one of those, so I'm not going to raise it to a power. And then I'm going to divide that by the reactants, which is HI. And that one does need to be raised to the second power because there's a 2 in front. So that's our equilibrium constant expression. All right, so now since I solved for these, I can plug that in. So Kc equals, our concentration of I2, we were told at equilibrium is 0.300. That's where our X came from. So I'm going to write that down. Okay, and then our concentration of H2 is the same because it was also equal to X. And then we're going to divide by the calculation that we solved for HI when we did 0.75 minus 2 times this 0.300. We got 0.15, but we need to square it because of that 2 in front. And that's what our expression says to do. Okay, so now you can type in numbers. So 0.300 times 0.300 divided by 0.15 squared. Okay, so I got 4. Okay, so I'm going to go ahead and use 2 sig figs because that's what the least amount of my givens. So Kc equals 4. Now I also asked for the equilibrium concentration of HI. So the way you're going to list that is HI, and you're going to put it in brackets because it is at equilibrium. The concentration of that equals, and that's what we solved for, 0.15 m. So those are my 2 answers. You must label it, okay? If you just write 0.15 m, I don't know what's equal to that. You're gonna lose points, okay? You must label what 0.15 m equals, and then your Kc equals 4.0, okay? So not all of them are gonna be exactly the same, but most of them will take up quite a bit of space on your paper. We are gonna keep adding to this idea, so make sure that you get really good at it and ask your questions if you have them.